All right, it is 10, so we will get started for today. So the grades for the test are up. Right now, you cannot actually see your old test. I should have that up in a little bit here, where you can go back and check your test and see what you got wrong and see what the right answer was. As I said at the very beginning of the course, I will drop your lowest test. So what I will do to see your most current up-to-date grade, I will update which test is dropped. I'll probably do that tomorrow, where I'll drop either test 1 or test 2 for you. So you can see your updated grade, your current grade in the class, if with the lowest test dropped. With that, though, other than that, let's get on with it. And we are picking up where we left off on Friday. So I am still on Friday's lecture. We just have a couple slides to go through here, and then we will go on to the lecture I have for today. So just a reminder that what we've been talking about is kinetic molecular theory. That is, how can we explain the behavior of gases? And remember, we have 3 assumptions for this. 1, gases are so small, they don't actually occupy volume. 2, that the hotter you get, the higher the average kinetic energy increases. 3, collision of particles are elastic. You don't lose energy, but you can transfer energy. So those were our 3 assumptions. But in actuality, real gases don't behave like kinetic molecular theory. In reality, gases do have size. Gases do take up space. Now, at low pressures, this doesn't matter. And you can't see what this says on the bottom. This is the x-axis is pressure in atmospheres, right? So at low pressures below like 200 atmospheres, and I should explain what we're seeing here. Here, we're looking at molar volume versus pressure, so volume versus pressure. The red line is what we calculate from the ideal gas law, and the green line is reality. Now, if we're at a pressure below 200 atmospheres, it's basically the same thing. The ideal gas law can predict the volume of argon. But as you go to higher and higher gas pressures, these 2 lines start to diverge. Our assumption, the ideal gas law assumption, which is based on kinetic molecular theory, starts to break down. That's because the ideal gas law still says, well, these particles don't actually have any volume at all, while argon does have volume. And when higher and higher pressure is applied to these atoms, they come into closer and closer contact, and they start to repel each other. And that's why we get a discrepancy in molar volume at high pressure. So short story is, ideal gas law is good for most conditions. Once we get to more extreme conditions, very high temperatures, very high pressures, either very high or very low volumes, right? Then the ideal gas law starts to break down, and we have to make a new type of equation. Oops, let me get out a pen. And this equation is called the van der Waals equation. And what the van der Waals equation is, it's like the ideal gas law, where we have PV equals nRT, but we have these extra corrections that are added onto it. So we correct for the gas molecules interacting with each other. That's what I mean by intermolecular forces. It's forces between different atoms. And we also correct for the volume that the gases have, where these A and N and B terms, A and B are constants that are determined for each individual gas. N is moles, B is volume. And what we can see here, here's PV divided by RT versus pressure. And again, at low pressures, no matter what gas you're looking at, PV equals nRT does a pretty good job at predicting how those gases will behave. But as soon as you increase the pressure, depending on what gas you're looking at, PV equals nRT gets worse and worse and worse. So if you really want to describe how a gas works, you need it to be really accurate. You have to use a better model, and that's this van der Waals equation. So that's how it's different than the ideal gas law. Now for the van der Waals equation itself, I'm actually not going to have you do this problem. So just for the sake of time, we're not actually going to use the van der Waals equation, but I do want you to know how the van der Waals equation is different than the ideal gas law. And that's what I just said. Van der Waals equation does account for intermolecular forces of the atoms, the interactions between atoms. And it does account for the volume of an atom. And the van der Waals equation is more accurate than the ideal gas law. But the ideal gas law is perfectly fine for 1 atmosphere, 2 atmosphere type of calculations. So is there any questions about that information? Well, we need it for test 3. Yes, this is all on test 3. You'll need to know what I just said for test 3. All right, so there are no other questions. Let me switch over to the slide I have for today, which we're going to be talking about energy now. So getting into new topic, saying goodbye to gases, hello to energy. Now let's start with some definitions first. So what is energy? Energy is simply your capacity to do work. The more energy you have, the more work you can do. So what's work then? Work is force acting over a distance. So imagine that you are standing still and in each one of your hand, you have like 20-pound weights. If you aren't moving, you aren't doing work. But as soon as you start moving those weights, you are doing work. So work, you need to be doing a distance, some kind of distance, some kind of movement, right? So energy is the capacity to do work, and work is force acting over a distance. And another type of energy that we'll often talk about in this class is heat. And heat is simply the flow of energy caused by difference in temperatures. Which direction does energy go? And we have 2 different terms. We have exothermic and endothermic, right? So when we talk about energy, we have 2 different definitions. We have the system and we have the surroundings. And I guess there's actually 3. We have the system, we have the surroundings, and we have the universe, right? The system is what we're interested in, is what we're actually looking at. The surroundings is everything that's not the system. And the universe is simply just everything, right? So the universe is system plus surroundings. So when we talk about heat flow, if heat is leaving our system and going into the surroundings, this is called exothermic. One way to remember that is exit rather. Exothermic exits the system, while endothermic goes inside the system, endo. So exothermic, so exo is heat leaving the system. Endothermic is heat going into the system. And this is simply done by difference in temperature, right? If the surrounding is hotter than the system, energy will flow from the surroundings to the system. So that's what's happening when you feel hot. The heat, the energy from the sun is going into your body. While if it's cold, that means that the outside is colder than you. So heat leaves you to go into the surrounding, and we feel that sensation as being cold. That's all exo and endothermic. What's considered a system? Anything that you are looking at. So imagine that I'm going to drop my pen. My pen's my system. Imagine I'm throwing a ball. Well, the ball is going to be my system if I'm talking about the energy. It's you define the system. It's whatever you are interested in. And the system is usually defined in a problem like, what is the change of energy when I explode gasoline? Gasoline's my system, right? Because I'm talking about the energy change of that molecule. So you usually, when you're talking about that, the first thing you do is just define what is my system. And we'll look at that too. So we have 4 different types of energy that we're mainly focused on. It's really only 3 types of energy. Actually, it's only 2 types of energy, but what we're doing is we're just kind of expanding our definitions a little bit. So we have kinetic energy. That's energy of motion. We have thermal energy, energy due to temperature difference, or energy of temperature rather. Potential energy, energy of position or composition, and chemical energy, which is potential energy due to bonds. So I say there's only 2 types because really thermal energy is a type of kinetic energy and chemical energy is a type of potential energy. But you can make more fine-grained definitions. So an example of each. So I'm holding my pen right now above the ground. The higher you hold it, the more potential energy it has because of gravity. As soon as I let that pen go, it's going to drop, and that potential energy goes into kinetic energy, the energy of movement. So all that energy I stored by having it higher and higher in the air, it's going to turn into kinetic energy when it moves towards the ground. While potential energy or chemical energy, our example there on the right is gasoline. Because of the bonds of gasoline, those bonds have a lot of energy. And when we break those bonds by using fire, we release that energy. And we can use it to do things like move a car, for an example. So chemical energy is the energy stored in chemical bonds, but it is a type of potential energy. So like we did on the pressure and gases, we're just going to start getting used to units of energy. So our first question is, let's say that you went to McDonald's. You decided to get a number one with a medium Dr. Pepper, which is Big Mac, fries, medium Dr. Pepper. That is 1,080 calories. I want to know how many kilojoules this is, because kilojoules, or the joule, is the scientific unit, or the SI unit of energy. Americans, we talk in calories. Scientific community, our unit of energy is the joule, right? So tell me how many kilojoules this is. And B, if an energy efficient light bulb takes 23 watts per hour to run on, how much or how many hours can I run this light bulb with the meal I just ate? So I'm going to get warmed up with some unit conversion here. If you have questions, let me know. Otherwise, I will be back in a little bit to work this out. All right, so hopefully we got a little bit of time to do that unit conversion stuff. At least A. Hopefully at this time in the course, A is becoming somewhat familiar how to do these. So let's get our good old train tracks out. We have 1,080 calories. For every 1 calorie, that's 4.104 joules. And for every 1,000 joules, that's 1 kilojoule. So calories cancel out, joules cancel out, multiply everything on the top, divided by everything on the bottom. That's 0.2632 kilojoules, or 263.2 joules. So that's A. So that's doing our conversion from calories to kilojoules. B, how many hours can we run a energy efficient light bulb? So here we want to go to the watt. So we have 1080 calories again. For every 0.860 calories, I have 1 watt. So that conversion hopefully is easy enough. What might have thrown you off though is how we get from a watt to time. And that's where our conversion comes in of our light bulb. So our light bulb is 23 watts for every hour. And right now, my unit is watt, and I want to be an hour. Here's our conversion factor. Right, for every 23 watts I have, that is 1 hour. That's how much energy it takes to run a bulb for 1 hour. Watts cancel out. I'm in units of hours, so I probably did my conversion right if I'm in a unit of time. So take everything at the top divided by everything at the bottom, and this would be 54.60 hours, or 54 hours and 36 minutes. Because the way I got 36 minutes is that you take 0.60, which is 0.6 of an hour, multiply by 60 minutes to find out how many minutes you have. You got 4.432. Let me double check. Oh, I did division, not multiplication. My bad. Yeah, 4.432. I put a divide sign instead of a multiply sign. 432 kilojoules. There we go. Thank you for pointing that out. All right. Any questions about our units of energy? Mainly the joule, but here in America, you're going to see it as the calorie when you look at foods and stuff. And when you look at energy for your house or your apartment, that's the watt. So a lot of different units, mainly all saying the same thing though. All right, we can move on. There's no questions. All right. So we're going to continue our talk about energy. Why did you start for cal for B and not watt? Because my foods and calories, and I just converted that to watts. I guess you could work backwards and find out. I mean, the other way to do it, I guess, would say, I have 23 watts and I can convert that to how many calories per hour and then figure out how many calories that is for A. That's perfectly fine. Both way works as long as you get the same answer. Yeah. So we have this idea of internal energy. So what is internal energy? It's the energy inside of your system, and it's kinetic plus potential. So at the very beginning of this lecture, I said, we're talking about 4 types of energy. And I said, that's really only two types. Yeah, so there are two types of energy. You can talk about the different subtypes, but there's only kinetic, energy of movement, and potential, energy of position. And so the energy that's in a particular system is just simply how much kinetic you have plus how much potential you have. For chemistry, when we actually talk about energy, it's going to be like molecules. It's going to be elements. So we're really talking about, how much energy is due to all the particles of our system, right? But just remember, internal energy is the sum of kinetic plus potential. And internal energy is this thing that we call a state function. And what a state function is that it's what we call path independent. That is, if you want to calculate a change in a state function, you just need to know the value at the beginning of your calculation, or what we call initial, and the value at the final. So what do I mean by path independent? All right, so let's say that you're hiking a mountain. And there are 3 people hiking this mountain. Person 1 goes up this path, goes up a switchback. Person 2 just goes straight up. They don't need a switchback. Person 3, let's not use Brown because Brown's the mountain. Person 3 hires a helicopter. That's my helicopter, folks. You're welcome. There we go. So person 3 hires a helicopter, flies up, and gets dropped off at the top of the mountain. And when looking at internal energy, the energy change for all 3 people are the same, because they all started at the same place. They all started at the same elevation. So let's say they all started at 0 feet above sea level, and they all went 20,000 feet in the air. So when calculating their change in internal energy, their initial state's 0 and their final state's 20,000. So their change in energy was all the same, if we're talking about internal energy like that. So to calculate changes in energy, by the way, if you've never seen this delta before in a mathematical equation, this is delta. Anytime you see delta, it just means change, right? And change in energy is always the final state minus the initial state. And for chemistry, we talk about reactions. So the change of energy of a reaction is the products, the energy of the products minus the energy of the reactants. And in case you're not quite sure what a product and a reactant is, let's have like molecule A plus molecule B goes to molecule C plus molecule D. All right, that's our chemical reaction. Anything on the left-hand side of the arrow is a reactant. Anything on the right side of the arrow is a product. So that's how we define reactants and products in a chemical reaction. And the change of energy is products, energy of the products minus energy of the reactants. All right. So any questions about our definitions of internal energy or state functions or how to calculate energies? All right. Moving on. So we already talked about this, but let's look at this a little more mathematically. So any energy that goes into our system has to come from its surroundings. So this is really talking about thermodynamics. And the first law of thermodynamics. So the first law of thermo is that energy is conserved. It can't be created. It can't be destroyed. It can only change the type of energy it is. So when we're looking at a system and we calculate the energy change of the system, if the system has gained energy, then it must have come from the surroundings. While if the system lost energy, that loss of energy must go into the surroundings. So the way we talk about that is if we have two different energies, energy system and energy surroundings, right? What's my change in energy of my system? What's my change of energy of my surroundings? We have this mathematical equation. Delta E system, change in energy of my system equals negative delta E surroundings. So let's say my system gained 200 kilojoules of energy. That must mean my surroundings lost 200 kilojoules of energy because that energy gain had to come from somewhere. It came from my surroundings. If my system loses 50 kilojoules of energy, my surroundings must have gained that same amount of energy. So that's what we mean with that mathematical equation. And that's basically what this whole slide is saying here. Energy is conserved. Yeah, that's a C. And so here on what this image is showing is here's reactants to products. Here our reactants were higher energy than our products. And remember, when we calculate energy, change in energy, it's always products minus reactants. So if we went down, our change in energy was a negative number. That means we lost energy in our system and they must have gone to our surroundings. So delta E system in this particular reaction here is negative, which means our surroundings must have been positive. They gain that energy, right? So if you lose energy, it's negative. If you gain it, it's positive. The system and surroundings must have the same value, just opposite signs. That's what this slide says in a nutshell. Any questions about that information or that idea? All right. So here's a question, and I have a poll for this because you have one of two options. So A, if energy flows out of the system and into the surroundings, what's the sign of delta E system? Is that endothermic or exothermic? And then B, if the internal energy of the products of a reaction is higher than the internal energy of the reactants, what's the sign of delta E? is endo or exo. So let me see. Get this poll. So here my poll options are only endo or exo. So just tell me in the poll, do you think this was an endothermic or an exothermic reaction? And then see from that if you can determine what was the sign of delta E. For this, I always find it very helpful to draw pictures and draw arrows that show me where the energy is going. I find that very helpful. So see if you can figure out what's going on here. Are we dealing with endo or exo? And that should tell you what the change in the sign is. So take a stab at that and let me know if you have questions. All right. So it looks like we have number one pretty comfortable. Number two, little more of disagree there. So I'll just do A super quick here. So A, here's our picture. That's our system. Here's our surroundings. So energy is flowing out of the system and into the surroundings. So it's exiting. So that's exothermic. And if it's leaving, that means overall the change in energy of our system is negative, right? Because energy is leaving. So it went down. So that's negative. So B, so the internal energy of our products of a reaction is higher than the energy of the reactants. So let's remember our equation. For delta E of a reaction, it is the energy of the products minus the energy of the reactants. And to help, I'm just going to put some fake numbers here, right? So if the energy of the products is higher than the reactants, so let's say the energy of the products is 100 and the reactants are 50. Completely fake numbers, but maybe with numbers that can help you with these type of problems. So 100 is bigger than 50. Okay, yeah, that would work. So products, if it's 100 minus reactants, which is 50, delta E reaction is 50, let's just say kilojoules. So my reaction, the energy went up 50 kilojoules. So here's my system, my surroundings. The only way to gain energy is from absorbing it from your surroundings. So this is endothermic. That's a positive change in energy. And this idea of endothermic and exothermic, we use these actually in a product you're probably aware of. So you know those like gels or whatever that you can buy to put in gloves and you crack it and then they release heat. What you're doing there is you're mixing two chemicals when you do that crack. There's a plastic layer that surrounds like a salt and water. And when you crack it, you're allowing these molecules to mix, and it's an exothermic reaction. And so heat is being released from the mixing of these chemicals, and we feel that as warm. While something that's like the opposite, where you crack it and then you put it on like your knee or something and it feels cold, well, that's an endothermic reaction where you're mixing like a salt and water. and it's taking heat from the surroundings. Well, if the surrounding is your knee, it's taking heat from your knee, and that feels cold to you. So that's how those products work. They're just endothermic and exothermic reactions by using different salts with water. Bath bombs are an endothermic reaction. That bath bombs depends how you define it, because bath bombs aren't heat, they're entropy. So they're, yes, if you're, as long as you're not talking about heat, so it wouldn't be like they're cold when they dissolve, are they? Oh, I guess I've never felt the temperature of a bath bomb then. If they're feeling cold when they dissolve, yes, that would be an endothermic reaction. Oh, okay. Cool, cool. I learned something today. I thought that was mostly just due to entropy. All right. So any questions about our definitions here? All right. So let's talk about the ways we can exchange energy. We've been talking only about heat so far, but there's another way to exchange energy, and that is work. Remember, work is force over a distance, while heat is really due to temperature. So heat, Q, anytime you see Q and it talks about energy, Q means heat. I don't know why it's called Q, but it is. So Q is heat. W, that makes more sense. W is work. So the change in energy is equal to heat and work. Now, heat and work are not state functions. What that means is when we're calculating heat and work, we have to actually look at the path we take. And that might not mean a lot to you right now, as the idea of a state function is probably still new to you. But what that means is we can't just look at the final condition and the initial condition and know like how much heat was lost or how much work was done. We have to look at every single point along the path we got from one area to another. So a way to think about this, again, imagine you are holding up you have your arms down by your side, and in your right hand, sure, you have a 20-pound weight. And then you just lift it in a straight line above your head. That's path one. Path two, you have that 20-pound weight again at your side. And instead of lifting straight up, you did like a zigzag all the way back and forth, back and forth, back and forth, back and forth until you got to the top. Path two is going to do a lot more work than path one, because path two, you move that force over a much greater distance going back and forth than path one, which you just went straight up. So that's why work is not a state function, because it is based on distance, right? So the beginning and the end point of my two examples are the same. And I guess I can draw that out in case you have a hard time like visualizing stuff. So like path one was I start down here, I go up here. So that's path one. Path two was I start at the same place, but I'm zigzagging till I get to the top, right? So the change in distance, initial and final, was the same, but the paths were greatly different. So path two went a much greater distance, which would mean a much greater change in work. That is to say, work's not a state function. Heat's not a state function. They are path dependent. But when you add them together, you do get a state function, which is energy. So even though I did all this wonky stuff, The change in energy of both paths is the same. It's just the amount of work done was different. So using the helicopter example in the straight up, since they were both going straight up, would the helicopter be less work? Taking the helicopter path versus walking up the mountain, if you're talking about strictly work and not talking about like heat or anything, so that one's a little weird because it comes down to the definition of the system. If you're talking about like the human does more work climbing up the mountain than riding in the helicopter, because when you're going up the mountain, you are fighting against gravity using your muscles. While if you're talking about the human who goes up the mountain versus the helicopter does more work because it's heavier. So once we get that's why those like little examples I gave, once you get into like more advanced physics, they kind of break down. So to answer your question, it depends on what you're looking at. I won't ever ask you something that like complicated on the test. That's just a fun thought experiment. But just know that work and heat are path dependent, while energy is not. Energy is what we call a state function. Heat and work are not. Path dependent is the distance. Yes. For work, it's that. For heat, just know that we cannot measure. For heat, it would be like, let's say, I have an, I don't know. I have a thermometer. Would that work? Nah, let's just say I have like a couch. Sure, a couch. And this couch is originally at 25C. And then like I took all the heat away from it and went to minus 10C. And then I decided to heat it back up. Now it's 80C. Now I have an 80C couch for some reason. While couch number 2, it was at 25C. Then it went to 80C directly. The path for heat is just like all the temperatures in between that I touch. So path 1 was a much greater heat change than path 2, even though the initial and ending points were the same. So that would be like an example of a path dependence for heat. And Gen Chem 2, you talk a lot more about this. You actually do calculations for this path dependency. For right now, we're just kind of focusing on, what does it mean to be path dependent and independent. So just some signs here with heat and work. If you gain heat, that's positive. If you lose heat, that's negative. If you get work done on you, I know that's a weird thing to say as a human, but let's talk about this. So here, the easiest thing to talk about is a spring. To do work on a spring, if you compress the spring, work is being done on the spring because you have to push it down. So that would be a positive example of work. And then when the spring releases, it's doing work on the system. It's pushing like gas molecules out or pushing something else away. So that's negative. So this is pushing down a spring, and this is letting a spring release. And that's our examples of work. Then delta E is simply Q plus W. So energy flows into the system, positive, flows out, negative. So those are some like examples of work, some examples of heat, some examples of paths. So any questions about those ideas? All right, so it is 10:50. What's going to happen is on Wednesday, I have a couple questions that really relate directly to test your understanding of what heat is, what work is, and what a positive and negative change in heat and work are. So that's what we'll pick up on Wednesday. It'll be a good review for what we just went over. As always, I'll put up a homework to get more practice on some of the calculations and ideas we went over today. Otherwise, that's it for Monday. Hope you have a good rest of your week. As always, if you have questions, feel free to email me. Otherwise, I hope to see you all on Wednesday. Have a good day, everybody.